Hey, it's Andrew, and I'm ready to talk about my, what is it called? Formation video series in detail because let's just face it, it just looks weird because in the beginning there's a different types of topics, different types of ideas kind of. Because formations what they deal with is they're just thoughts, they're just experiments when it comes to different math properties. And I know that it does have parallels to other stuff like vectors, matrices, lattices, like for grids. And despite my lack of knowledge on those topics, it is so fun. Just going outside the box of your average classroom. And even though I'm taking AP calculus, there's a lot of ideas that can be done. I'm trying to be inventive, trying to show things in a different way. That's what formations are about. And it's not like just being self-centered. Like this is my formation. No, no. What formations are? They're just there just to show others like, hey, like this is my approach. This is some sort of alternative. And in that way, it makes sense. But there's the flaw. The big flaw is that for formations, there are like the ones I'm doing. It has a lack of basis. Like why are you confident about this? There are things that in the video that you don't manage to make detail on, like what defines your concepts. And with that matter, I'm going to redefine grids. Grids, they are a set of real numbers that are specifically oriented. So what this means is that they are put in a specific order. Well, okay. I guess that was I'm just repeating stuff at the moment. So grids are represented as this. So there's a number or some sort of indicator that's a group G or a grid G. Not to be confused with the group. So R times C and then A1 all the way to A sub n. So grid, this is the name, then this is the row, column, this is the first, let's say this is the first input, and again I'll call it a slot. This is the nth slot. So slots, they're the outputs of the grid. So before we talk about what slots are, we need to know about the criteria of the grid. What makes a grid? Step 1, or condition number 1. So the must be rectangular with dimensions R times C. So we know what R and C are, such that R and C don't equal 0, and R and C are in the set of positive integers. And it makes sense because the rows and the columns, they shouldn't equal 0 because that wouldn't be a grid. It wouldn't be a rectangle. And we'll get to that later. So condition number 2. We have this grid and there exists A of n such that A of n or any A of n is in the set of real numbers. So that goes with this idea that there are real numbers going in a grid and it deals with the operations. So right now, the third criteria, number 3, indicates that a transformation where G transforms to G, the structure has to change, or it has to remain the same, but in a way where, okay, if that changes, that means the rows stay the same, so in a way they stay fixed, the columns stay the same too. So only if, only if G, let's see, I see. So this is the final property. So this so that condition exists only if this G of R1 C1 is equal to, hold on. Okay. G of R1 C1 is equal to another grid H R1 C1. Right here. It managed to have a one-to-one correlation. It's similar to a bijection of a group, which is an isometric group. So for a grid, it has very similar properties to a matrix. And in a way, a grid is more of a simplified but strict. It's a strict version of a matrix. And for matrix or matrices, they're for general uses. And I'm sure that there are a lot of uses today which are still applicable when it comes to solving linear equations. So it's more directed for linear algebra. And with these two claims, of course, there is a hint of linear algebra in a grid. And it comes towards the third law, which is about the operations. In specifically scalar operations. And dealing with, okay, this is the first law, kind of like the same size. So when you're adding and subtracting matrices of the same size with the same dimensions, then of course everything is going to go with a one-to-one correlation. This is what I've been talking about. So each entry has a place to go, and it's in the same kind of order. And they're technically not coordinates, but I see how a one-column matrix can be represented as a vector, which is 1, 2. Let's say a vector A. And for scalar multiplication, if you multiply this vector by 2, then you get 2 and 4 for the components. And yeah, it's very similar to what you can do with the grid. Instead of using coordinates in the coordinate plane, we're just using the basic locations of an array. So in that way, it's a lot more visible, a lot more simple, but of course matrices, they're the thing that you should go to. So as for matrix, or for a matrice, it has an inverse. And I know it has to deal with a determinant. Or maybe there's more than one way to find the inverse of a matrice. And I know when you're dealing with a 2 times 2 matrix, it's AD minus BC. Such that, yeah, of course, A, B, C, yeah, of course, they're in this matrix M. This is M, where this is A, B, C, and D. And I know that the inverse of this 2 by 2 matrix, well, technically, okay, maybe they're not correlated, but these are two different things about a matrix. It can be used or not, depending on what you're using. So I think it's when you switch the D and the A, then you make this negative. Something like that. That would be the inverse of M. Yeah. The grid's inverse is when we're dealing with a binary grid. So this is when x, so the possible values of this x, which are the slots, the possible outputs, are 0 and 1. And that we know that, yeah, of course, x is in this grid or matrix M. And then we can find the inverse by switching 0 to 1, 1 to 0. So 1, 1, 0, 1 is transformed into 0, 0, 1, 0. And it kind of, yeah, you can see how it's going, but I don't know, you might get confused with these two things. So it's good to transition thoughtfully, and I hope it would help. Like I didn't know it at the moment, but hey, the more you know. Okay, we talked about the determinant, about the inverse. Now let's talk about the rectangular shape. It looks very, very convenient. So when you're dealing with looking at a matrix, of course there's this, what is it called, a notation. When we're dealing with A, and you can just do IJ. Okay, it's kind of like the row and the column thing, and I liked how I did with my R times C. And of course that works. But what I'm also dealing with is the kind of set notation. So when we're dealing with this one right here, A, B, and C, and D, it can be a set where it would be A, comma B, comma C, comma D, in which the first two elements are the first row, or are in the first row, and then the second, or the last two elements are in the second row. Same with the first and third, which would be in the first column, and then the second and fourth, which will be in the second column. It would be much easier to even write in the first place. So both of these kinds of structures, they are rectangular, they are not circular or rotund. Either way, circular, triangular, it's neater looking towards the rows and the columns. So this is the first, in a way this is the first law. Yeah, same size, scalar. Yeah, that would be the third one. As for the second law of what a grid can be, I can say that a grid, yeah, both of them, they include the real numbers, and so forth. It's pretty, yeah, very similar.